Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. This is for my integrated Math 1 classes here. Now this is being recorded on a Sunday. Generally I would do Fridays, but my Friday was pretty booked up. In fact, my yesterday was pretty booked up as well. Or it was just weekend time. Now it's time for me to go ahead and get this recording in. Every 2 weeks I try and do one of these for my students. It's been quite a while because they did some testing, had some weeks off. There was actually a good stretch where I had a little issue with my gums and such. I didn't want to talk a lot. So anyway, here we are, Power Hour. I only have very few, 6 questions. Same with Integrated Math 2. Only 6 questions to go over with you guys. Let's go ahead and see what they are. The first question here asks, why does the Pythagorean Theorem always work? It's actually kind of funny. So this is something that I kind of encourage some of my students just ask me. I said, this is a good Power Hour question. You can trust it for now. I'll tell you what it is, but you know, what's the proof? And it's just kind of a funny thing because I was sitting there thinking about, there's one thing, we haven't done quadratics yet with squaring things with polynomials. So there's, if I do the proof, there's a part of it that you might also just have to accept as truth. And I have to construct it as well. I didn't know that this was going to be a question in the Power Hour, and I'm saying it right now. So here's how the construction works. It's kind of strange here, but I'm going to build you a rectangle. Okay. No, a square. It has to be a square. I'm going to build you a square. Within this square will be another square that inscribes it. It's got to be touching. Let's see if I can do this right. Obviously, it helps to see the question before, but it should be kind of touching all the sides like that. Now, the properties of a square are as such that you have all right angles, all equal sides, and the area of a square is base times height or squaring any one of the sides since they're all the same. Now within this breakdown right here, I'm going to give you some lengths. Anytime, so these are right angles here. Anytime you have, so all of these are equal. This is equal to this, is equal to this, is equal to this. The nature of the squares make that so. And then this is equal to this, is equal to this, is equal to this. And then these are all equal to each other as well. So I'm going to give them values, and we're going to call any of the shortest sides A, any of the longer legs here B, and the inner parts here C. Okay, now within here, guys, you do have right triangles. For example, this right here is a right triangle. Now there are 4 of these right triangles here. Hopefully you can agree to that. There's one, here's another, here's another, here's another. And again, they're all equal in leg length, hypotenuse length, and area. And we're really going to be talking about area stuff here, okay? If I looked at the entire big triangle, square, excuse me. If I'm talking about the entire big square right here, there is an area that I can define for this square just by the side lengths alone. Each side length is a combination of B and B plus A plus B I should say, right? It's the segment addition postulate. A plus B is this entire length. This entire length is also A plus B. So if I want to take the area of the entire square, I can do one side length times the other side length, or of course squaring it. A plus B quantity squared. That's one way to represent the entire area of this thing. Here's a second way to represent the entire area. Add up the areas of each individual part. This square here, C, and these 4 triangles. This one, this one, this one, and this one. If I add these 4 triangles with this inner square, that's also equivalent to the area of the square that I got through another calculation. So this will equal, what are they? I have 4 different triangles of A and B as if B, sorry, I'm speaking, I know what I want to say, I'm trying to think how to say it to you. To find the area of a triangle, it's 1/2 base times height. So I'm going to do 1/2 base times height. I can do A times B because A can be my base and B can be perpendicular to it, okay? That's the area of all 4 triangles, 1/2 base times height, and then there are 4 of them. Plus, the area of this square is C times C, right? C squared, like that. All right, so it's a lot to kind of talk about here. Now, here's the part that you're going to have to kind of accept here. A plus B quantity squared does become A squared plus 2AB plus B squared. That's what, it doesn't just become A squared plus B squared. There's an inner part, and again, I'm not going to get deep into that right now. 4 times 1/2, guys, is 2. So this 4 times 1/2, that just becomes 2. So this becomes 2 times a times b. So that's 2ab plus c squared. Now if I subtract 2ab from both sides here, minus 2ab minus 2ab, the 2ab's cancel out right here and right here. And what are you left with? A squared plus b squared equals c squared. And where do A, B, and C exist in any of these? Well, look back at this triangle I was drawing before. A and B referred to leg lengths of this right triangle, and C referred to the hypotenuse. So a proof, guys, a proof is a way that you can kind of work things out so that they apply. I didn't use any numbers here. I mean, I used the 2 and the 4, but I didn't use numbers as examples. I use this thing to say in any situation where you have a right triangle, there's a way to kind of dictate how the leg lengths and the hypotenuse have a connection with one another, and this is it. This isn't something you have to know. I don't think you'll ever have to know it, but understanding the concept of, excuse me, how proofs work, just an idea that proofs are a thing. Understanding the concept that there's no way around this bit. And by the way, the theorem, the Pythagorean theorem states that in any right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. It's also true, the converse of it is also true, which means if the sum of the squares of two sides in a triangle equals the square of the third side of the triangle, then it is a right triangle. So there's no way around this dodging this Pythagorean theorem for right triangles in any sort of way. In every right triangle, a squared plus b squared equals c squared. And for every triangle where a squared plus b squared equals c squared, it's always a right triangle. There's a little more that even my IM2 kids, I don't think are learning with me or anything. At some point you might. But if a squared plus b squared is greater than c squared, then you have an acute triangle. And if a squared plus b squared is less than c squared, and if it's still a triangle, then you have an obtuse triangle. Kind of neat stuff. But this is a right triangle. There's your proof. Thank you for asking it. I am moving onward. Okay, next question says, when we have a line like of AB, and we know two of the numbers, why can't we just subtract them to get the last number? Well, I don't know exact question. My guess is you're asking why I'm making you particularly add first to show subtraction later, and part of it's to make sure that work's shown. Let me see if I can set this up for you as far as what you might be asking. I don't know if this is actually it. Let's say I have a segment here. Let's just call it AB, and then there's some value in AB. There's some value in the middle, let's call it M. Not necessarily midpoint, but just right there. And let's say I knew that this was 10, and this was unknown, and you knew that the whole thing was 25. And then I'm trying to ask you to solve for X. I guess, my guess is you're asking, why can't you just say 25 minus 10 equals 15, X equals. And I mean, honestly, and in a lot of respects, you can, C-A-N, you're allowed to. What I'm trying to make sure is the connection here, because a lot of things get lost along the way, and I'll show you an example where you really might mess it up. But what I want to make sure that I'm seeing work-wise is a scenario where you're making sense of the actual form of what's called the segment addition postulate, and the word in there is addition, which I need to know the understanding, the full understanding, that as you have collinear points building parts of subsegments right here, that the sum of these two segments add up to become the third thing. Subtraction occurs. I write 10 plus x equals 25, and how do I solve for x? I do subtract 10 from both sides. But I'm setting up the postulate to begin with here, right? I'm setting up the postulate to begin with here, and then going from there. It's the same thing like I tell my IM2 students as well. For any pairs of supplementary angles, if you don't know what those are, you're fine. But any pairs of supplementary angles, you first show me that they add up to 180. Just give me that, and then we'll work from there. I am trying to save your skin from making some mistakes, but at the same time, when with work shown, I'd like to see the algebra come into effect. There can be more difficult problems where it's not quite, just that easy. And let me just give you a second example. Let's say instead of this just saying x, let's say it said 9 minus x right there, and then you wanted to solve. Right. Well, if you wanted to play your subtraction game, here's where you might do something dangerous. You might say, time out. I actually didn't even want to put that there. Let's put x plus 10 here as well. 9 plus, I don't know. This is me doing an example on the fly. Let's do x plus 1. I don't really care. But anyway. I don't know how I want to solve this, but my point I was going to make was, let's say you take 25, well, now there are two sets of x's. My point I was going to make is I don't want you to subtract. Let's say I did this. This would be a true statement. 25 minus x plus 10 equals x plus 1. This is a true statement. If I subtract x plus 10 from 25, I get x plus 1. What someone might make a mistake of doing, I'm not getting the good example that I wanted, but what someone might make a mistake of doing is doing minus x plus 10 and not quantifying it. Now you're subtracting it in such a way that that 10 is never being subtracted the way it's supposed to. When I quantify it here, I may be adding 10 with the x, but as they're both being subtracted, the 10 ends up getting subtracted. So that's just one of the other things to avoid. Anyway, I can't get too deep into it. I don't know if that's what you're asking, but that's the way that I want to answer it. I just, for one, I do need to see the work. While we're distance learning for some of you guys, I just need to see the process. I need to feel out what's going on. I need to make sure that the work that I'm doing is not being lost, because there can be more complex problems like these, and this isn't very complex, but more complex problems like these where you just want to be secure, have to do more, and make sure you fully understand the postulate that you're covering. And I hope that answers it. I don't even know if that was the way that it was being asked. Okay, the next question is, can you give us some examples of coordinate notations and simply go over them just so we can get a better idea of the formulas? So we started transformations here at the end of last week, and I'm guessing you're talking about the actual rules, the rules that are applied. So if I'm looking at, and actually I have a graph thing just in case, and it's good I can use it. So I'm going to move this thing over. I don't know what I want to do as an example yet, but a rule could be if I'm transforming points from xy over to x minus 7 comma 2y, something like that. The basic nature of rules is if you have a set of points, let me make some up. Let's say this is A and B and C, like that, and we have to do a transformation. This, I won't end up being able to graph the next one, because it looks like if I double some of these numbers, they might get too large. But A is at the point negative 7 comma 5, B is at the point negative 1 comma 3, and C is at the point 1 comma negative 6. And we got to transform these. Well, now when you're saying can you simply go over them, I'll state that simpler might mean taking longer. If you want simple, there is a lecture video on it that's simple, but it's faster. So I mean, I don't know which way you mean simple. If you mean a way to make us make sense of it, or if you want me to explain as little as possible. Because I actually explained as little as possible in the lecture video. But here's the nature of this right here. And this is the part that can get a little troublesome depending on, and I'll change the example next time. Seeing these variables as x and y can get a little tricky, because you can't just think of them as x and y. These might as well say the letters A and B. It doesn't matter what they say. What matters is where are they over here, and what are you plugging in. Every value that's an x right here is negative 7, negative 1, and 1. That means anywhere that you see an x over here, you are going to plug those numbers in. The reason why I said it's dangerous to call this x right here is because it may not always end up in the x coordinate. Now, in this case it does, but let's check this one out here. If I want to find out a prime, b prime, and c prime, a prime here, when I take this x, negative 7, I substitute it in for x. X is negative 7, put it in place there. That's negative 7, and then I have a minus 7 right there. My b prime will be my negative 1. I plug in for x, and then I subtract, negative 1, and then I subtract 7. I don't really have much room here. And then I haven't done the y's yet, you can tell. And then the c prime, I'm going to take 1, plug it in, and subtract 7, right? So I'm going to get some numbers out from that. The y values that you see here exist right here is 5, 3, and negative 6. And I'm going to substitute those in for y. So here, if y is 5, I'm going to do 2 times 5. Here, when y is 3, I'm going to do 2 times 3. And here, when y is negative 6, I'm going to do 2 times negative 6, which I think gets out of reach. But that leads me to have a prime at negative 7 minus 7 is negative 14, comma, 2 times 5 is 10. And then I would plot that point. I'm not going to, but I would. B prime is at negative 8, comma 6. And C prime is at negative 6, comma negative 12. Again, a little out of reach. But that's where they go. So as far as instruction goes, you just follow those rules. Now, the thing that I'm continuing stating about danger and stuff is just understand that these x's, x is a variable, and you're substituting in for the variable. But the x coordinate, I'm going to go left 14 because negative 14 is the x coordinate. It's in the left place. And I'm going to go up 10 and plot that point like that. And the reason I keep saying that is because let's redo this problem, or let's do a different version of this problem. And in this version of the problem, instead, in changing the rule, I'm going to make it say let's do this. Negative y, comma, negative y, comma, 3x minus 4. Okay, well, the x values are negative 7, negative 1, and 1. The y values are 5, 3, and negative 6. And when I say x, y, I don't mean the coordinates. I mean the values. X is negative 7, negative 1, and 1. They are the x coordinates, but look where they end up now. They are in the right. They're in the y coordinate now. And that's the problem some people have is they see x here and they think, oh, when I plug it in, I'm going to go left and right. No, this is a y coordinate right here. This is something, comma, the y value. But I'm plugging in the original x values into here. So just as far as this goes, guys, the y value, I got to do negative y in the x coordinate. So I'm going to do the opposite of 5, negative 5, comma, and then I do 3 times my x value of negative 7 minus 4, and that a prime becomes, sorry, that was a prime. That a prime becomes negative 5, comma, negative 25. The point is, when I plot this point, just because x was in the y coordinate doesn't mean I go 25 to the left. No, this is a y coordinate, so I go 25 down. I go negative 5 to the left and 25 down, and I plot that point. I'm not going to continue this whole thing, but the simply going over is you simply substitute numbers in, and then you simply plot those points. That's the simple part, but I want to keep reminding you of just because something says x doesn't mean you go in x direction. It depends, is it x coordinate or not? But you substitute, and honestly, I would ask you to show work as well. Now, as far as the rule and everything goes with graphing, guys, of course, when you plot the point, you label it. So if a prime was right here, you call it a prime. Don't stop short of doing that. Anyway, that's all I'm just going to say on that. I don't know if I really covered it the right way, but I wanted to emphasize points that may not have made much sense the first time, and I hope that they kind of did when I did them there. Okay, plus someone else might ask more questions on it. Next question, is there any shortcuts to solve or to find points when we are finding the coordinates on a graph? Well, I wonder if that's more of the same question here. So far all we've looked at are the rules for transformations. We haven't even looked at names for different transformations yet. So I'll say when you learn more about transformations themselves, you might be able to do things without needing to calculate them. And yeah, I'm forcing calculations on you right now with the rules. But when you learn how to rotate 90 degrees clockwise about the origin and such, you might be able to do it without the rule. Personally, I'm not the biggest fan of the rules. I'm not saying I'm not. You need to know how to do them. And but as we start to do more rules later this week, you're not going to be able to memorize these rules. Heck, I can't. I couldn't tell you the rule off the top of my head for rotating 90 degrees clockwise. I'll show you how it appears in video form. But as long as you know how to follow the rule, that could be a shortcut. Another shortcut could be to literally know how to do it. I'll kind of give you more when you do transformations. If you're talking about just rules, though, by rules I mean the coordinate notation. No, there's not really a shortcut. Just plug in your numbers and get them out. I don't know. Yeah, that's kind of it. You'll see more on transformations this week, in which case I'm not going to call them shortcuts, so to speak. But there's more than one way to approach how to do a problem. I'll give you my own perceptual basis. It's easier for me to explain if we're physically in class on it. I wish I had a document camera in my class. That would really make it a lot better. But yeah, shortcut wise, it's nothing. Shortcuts are only for those who understand them. So make sure that you know that just because there's a shortcut there doesn't mean it's going to be easier, or that you will understand it as well. So when in doubt, there's always a when in doubt. Always seek the best way for you, not the quickest. Always seek the most efficient, something that you know how to do and is fastest for you. So I don't know. I'll explore all the options with you. I don't really know if that answers it, because part of the answer is not there yet. We need to actually learn some of the transformations. But regarding rules, no, it's not really shortcuts. Just plug them in. Make sure you know what you're doing. Plug them in, plot them. That's all. And we'll keep moving forward next week on that. Okay, how do you identify what type of transformation a graph is showing? So, like I said, I just answered in the last question. We haven't yet gone over them, but let me list out the different transformations that we'll be mostly paying close attention to, or at least I assume we will. If you're doing stuff this weekend, you probably already heard a bit on translations. And there are reflections, rotations, and dilations. Not going to get deep into these, but a translation is just moving an object. Like, here's me translating. Here's me translating, and oh, hang on, let me do this. Here's me taking this, and I translated it. It's just moving it. I have hiccups now. I hope I can get through this stuff. A reflection, and you know what reflections are, but a reflection would be something like this. You're like, what's this doing? These are different transformations. A rotation, oh gosh. Where's my water? I don't know if I have one. A rotation is doing this. There's a rotation. And a dilation is doing something like that. Anyway, those are the different kinds of transformations we'll do. Translations, reflections, and rotations are all rigid transformations. They keep the size and shape of the object intact. A dilation does not. There's another form, I won't call it dilation, but there's another form of a transformation. Oh, I can't do it. I'm trying to make it skinny or fat. It's not a dilation because not everything remains in proportion, but just stretching, growing, skinning. Let me find water. I have hiccups. 1 second. I'm still holding my breath. We'll see if the water worked. If not, I'm going to have to scare myself somehow with a video. Okay, so I hope that I kind of answered that question. How do you identify it? You got to know what it's doing. If your object just moved, it's a translation. If it flipped over. And you know what? A lot of people actually have trouble. I don't know how deep we're going to get into it, but people have trouble dissecting between a rotation and a reflection. I think I have enough video support to kind of talk about the difference between the two. I think I specifically use the letter F even in some of my videos because it's just a unique, all letters are unique, but they have specific points that you can talk about and show. And hopefully you can start to learn the difference between the two. It's going to take some time. Some people mistake one for the other. Just all the time. It happens. Anyway, I don't know if that really answered it there, but because we're getting deeper into it next week. And so I like you looking ahead without even knowing that you're looking ahead, but I like you looking ahead in that thing. And last question, how do you identify a non-rigid figure? Well, a rigid figure, like I just mentioned on the last question here, the different types of rigid transformations are translations, reflections, and rotations. It's where you take an object and reorient it somehow in space. You can even flip it over. But you saw the Spider-Man probably example from my videos. But reorient it somewhere in space where it might be facing a different direction, right? It might be in a different place. It might have even flipped over and been mirrored. But its size and shape are still intact. Spider-Man is still Spider-Man, just normal form and stuff. Once you change its size, like a dilation is a size change. Once you change its size, I think my hiccups are gone. Once you change its size in some sort of way, whether you stretch it, shrink it in either direction or in both directions, it no longer maintained its size and shape. So you're asking, how do you identify a non-rigid figure? Sometimes you could just look at it, and say like, clearly one is bigger. If I have two different, if I have a transformation of one figure from another, and I take, this isn't going to be exact, but I take like these three right here, and then I do some rule where now the transformed image looks like this, and it's obviously surrounding it. There's clear evidence, as long as you plot the points in the right spot, there's clear evidence that as it surrounds it, it must be bigger. But if I were to ask you to mathematically, I guess that's scientific, but if I asked you to mathematically conclude it, you'd have to show that any corresponding points have different side lengths and or angle measures. Since we're not talking about measuring angles, we could just talk about side lengths. So the way I would do it is if I had side length A, or side length AB right here, and side length A prime B prime after some sort of dilation, I guess. You could figure out these two lengths by using, the distance formula, the Pythagorean Theorem. Find out what this, especially on a graph, find out how far these two are. Do A squared plus B squared equals C squared. Solve for C. Do it right here again. A squared plus B squared equals C squared. Solve for C. When you find out they're two different numbers, I think that's enough. But, how do you identify it? It's really just about, did its shape, size and shape change? Did one corresponding side length, AB to A prime B prime, change its value? And I guess that's really all you're trying to do there. So they're not always going to be drawn though. Just understand that we won't always draw them. So if you're given the actual coordinate pairs, you might jump into distance formula instead, but just show that the side lengths are actually different when you do that. All right, so I think that is all 6 questions there. I sure hope that was enough for you guys when you asked them to make sense of it. I hope that I answered them for you, and I hope those who didn't answer, still kind of knew what they were going to do with it. So anyway, that's it for me, guys. Thank you so much. Take care.